In this video, we're going to extend Green's theorem to apply to regions in the plane that contain holes. All right, so to see how we could do this, let's suppose we have a region in the plane that contains a hole. Right? And so we're going to draw a very simple region here. Right? They can, of course, be more complicated than this. But we have this region that I'll call D. So we're looking at this annulus-looking region here. So for this region, the boundary consists of two curves. And in particular, two simple curves, which we can call C1 and C2. And we're going to assume both of these curves are positively oriented. Right? And so in this picture, we have on the outside of our region, we want this to go counterclockwise like this. So I might call the outside of this C1. And the inside curve there is going to be C2. But we have to be a little careful here. This is C2. We have to be a little careful here. We defined positive orientation before as being counterclockwise, but really the key is we want the region to be on the left, which with simple regions, like which is all the ones we've seen before, that simply means counterclockwise. And in this case for C1, it means counterclockwise. But if you imagine yourself walking around the curve C2 and ask yourself, which way would I have to walk in order to have the region on my left? You'd actually need to walk clockwise around this inside circle. And so this is the one little thing we have to be a little careful of, is we actually want to be, we want this to be the inside curve to go clockwise, right? And so that's what we mean by positively oriented for an interior curve, right? All right, so now what we're going to do is we're going to take this region with a hole and we're going to divide it into two regions, which we're going to call D1 and D2. Right? And the way that we're going to do this is as follows. I'm going to make two segments that go from the outer curve C1 to the inner curve C2. All right, so I'm going to draw this one here, and then I'll draw one over here. It doesn't really matter where they go. It just they have to go from the outer curve to the inner curve, and they cannot intersect each other. And I have to orient these so that one is going from C1 to C2. So I'll orient this one on the left, or on the right as going from C1 to C2. And I want the other one oriented to go from C2 to C1. So I'll do that on the left. Right, so now we see in this picture that doing this, we actually can split up this region D, into these two regions, D1 and D2. In a little bit, we're going to need to describe all the curves in this picture. So I'm going to go ahead and label them now while we have the picture in front of us. So the curve C1 on the outside of the circle is now broken up into two curves by these endpoints of the segments that I just added. So I'm going to break up those two curves and call them give them slightly different names. So if I look at the first part, starting on the right and going to the left, that curve there I'm going to refer to as C1A. It's the first part of curve C. The other part of it, the bottom part in the picture that I drew, I'm going to label as C1B. Right? Now, the A and B don't make any difference. I just need to denote the two different pieces of this curve, so I'm just using an A and a B. You can denote them different ways. That's how I'm choosing to do this. All right, we're going to do the same thing with C2. C2 is broken up into two curves by these two intersection points of those segments that I added. So I'm going to call the upper half of that C2A, and the bottom half of that will be C2B. Right, and then I also need to label these segments that I added. So the one over here on the left side, I'm just going to call C3, and the one on the right, I'm just going to call C4. Right? And the last labeling I want to do here is, like I said, I wanted to break this up into two regions, D1 and D2, and I've done that. I can talk about region D1 on the top and region D2 on the bottom. Right? And these two regions are all bounded by the curves C1A, C1B, C2A, C2B, C3, and C4. And notice that neither of those regions, D1 or D2, neither of them has a hole. The way that we've kind of added in C3 and C4 and broken this up into two regions, the whole point of this was to eliminate that hole from the region, but now we have two regions to consider. Okay. So if we wanted to compute the double integral over region D of del Q del X minus del P del Y dA, we want this double integral over the region D. We can simply take the double integral over region D1 of this particular function, del Q del X minus del P del Y, and add to that the double integral over region D2 of the same function. Right? And now D1 and D2 are both regions that are bounded by simple, closed, positively oriented curves. And so we can apply Green's theorem to each of these double integrals. So we can have the integral, I'll write down the curve in a moment, of P dx plus Q dy, plus another integral, again, I'll write down the curve in a moment, P dx plus Q dy. And the curves for each of these are going to be the boundaries of the two regions D1 and D2. Right? And so a analytic geometric way of denoting the boundary of a region is actually using the del symbol that we use for partial derivatives. So before I write these curves, I just want to point out that if I write this del of D1, this simply means the boundary of region D1. Right? And so even though this is the same symbol we use for partial derivatives, in context, it's not confusing. If I write del D1, D1 is a region, partial derivatives doesn't make any sense in that context. And so the double integral over D1 is the same thing as the line integral over the boundary of D1. And same thing here, the double integral over D2 is the same thing as the line integral over the boundary of D2. Right? So now we just have to simplify the sum of these two line integrals. So I'm going to use really bad notation here. I'm going to leave out the P dx plus Q dy because it's going to be the same. But I just want to break down what is the integral of over the boundary of D1, right? If we have a region like this with multiple, it's a piecewise smooth curve or a bunch of curves put together from end to end, we know that the line integral of that is equal to the line integral over each of those sides, each of those boundary regions or boundary curves. So the boundary of D1, if we go around in that picture that I had, we're going to have C1A, that's the first curve. And then we're going to have the line integral over negative c3. Now notice that we have to take negative c3 because in order to traverse it, we're actually traversing it in the negative direction against its orientation. So that would be the curve negative c3. Okay. And then after that, we take the integral of c2a. And then the integral, lastly, the integral of negative c4. Again, we're going against the orientation of c4. Right? And so again, this is terrible notation. All of these integrals are of that same function p dx plus q dy, but I'm just indicating here that in order to compute that line integral over the whole boundary of d1, I need to compute these 4 line integrals of that same function p dx plus q dy. Right? We can do something similar then for the boundary of d2. So if we go around d2, we see we have the integral of over c4, plus the integral over c2b, plus the integral over c3, and plus the integral over c1b. Right? In this case, the integrals over c3 and c4 are positive. We're going in the direction of the orientation, so we do not need the negative curves there. Right? And so we see what we have above is we actually have the sum of those two integrals, which are the sum of these two here. Notice that when we go to add these, we're going to have the integral over negative c3, and we're going to add to that the integral over c3. And those integrals are negatives of each other, and so when we add them together, the sum will become 0. And the same thing with the integral for over negative c4 and the integral of c4. So those values, whatever the value is, we don't know, but we know that they are going to be negatives of each other. So when we add them together, we get 0. Right? Also, when we add all this together, we're going to have the integral of c1a plus the integral of c1b. When we add those two together, we're going to get just the integral over c1. Right? c1a and then c1b, if we follow both of those in order, we get the entire curve c1. And lastly, we have c2a and c2b. When we add those together, we're going to get the integral over c2. Right? And so we get the punchline that the sum of these two integrals right here will actually be equal to the integral over c1 of p dx plus q dy plus the integral over c2 of p dx plus q dy. And so what we've shown here is that this double integral that we started with at the top of the screen is actually equal to the sum of these two line integrals, one over the outside curve of the region with a hole and one over the inside curve of the region. Right? And so this is another version of Green's theorem, which applies to regions with holes. So maybe I'll just call this the hole version. But it says exactly what we just described. And I won't go through and look at all the hypotheses here, but it's exactly the same as in the original version of Green's theorem, just now that we're allowed to have a hole in our region. But it simply says that the double integral over our region D of del Q del X minus del P del Y dA is equal to the integral over C1, the outside curve, P dx plus Q dy, plus the integral over C2 of P dx plus Q dy. And so again, we have to remember C1, the outside curve, needs to be oriented counterclockwise so that the region is on the left. And this curve C2 has to be oriented in the clockwise direction, again, so that the region is on its left. All right, so let's take a look at an example using this version of Green's theorem. So let's let C1 be any positively oriented simple closed path that encloses the origin. Right, so we have a very general curve here. We don't have any kind of information about it. The only thing that we know is, of course, that it's positively oriented, so it is going to be oriented counterclockwise. It is going to be simple. It's not going to cross itself. It's closed, so it's going to start and end at the same point. And the only real piece that we know, in addition to those basic assumptions, is that the origin has to be inside the region. It's the only thing that we need that we have. And so what we'd like to do is we'd like to evaluate the line integral over this curve C1 of the function negative y over x squared plus y squared dx plus x over x squared plus y squared dy. So because we don't have a specific explicit curve for C1, there's no way we could possibly evaluate this line integral as written. We be able to, if we could find a parameterization for our curve, we could apply it, possibly plug those parameters in and see if we could get something that we could integrate. But in this case, we don't have any way of parameterizing this curve C1 because we don't know anything about it. It could be a lot of different things. And so what we're going to do, I'm going to start by just looking at like an example. And so I have the C1. All I know about it is a positively oriented simple closed curve that encloses the origin. So it's got to look something like, well, it doesn't have to look anything like this, but here's an example of what it could look like. So I'm just going to draw this. It's a simple curve. It is positively oriented by how I've drawn my arrows. And the origin there is inside this curve. So this is a picture of what C1 might look like. Now, because the origin is inside this region, I know that there is some circle centered at the origin that lies entirely in this region as well, inside the curve. And so, for example, if I pick C1 to be what I drew here, I could pick this circle here and call it C2, right? And even if the curve C1 gets really, really close to the origin, because the origin has to be inside the curve and not on the curve, there's always going to be some circle that we can draw that's centered at the origin that lies inside C1. Right? So given this scenario, I'm going to let D be the region inside C1 and outside C2. So the region inside our original curve C1, but outside this circle that we found centered at the origin. And now we're going to apply Green's theorem. Right? And we can apply it to this region D because D is a region with a hole. Right? The area inside that circle C2 is removed from the region D. And so we have a region with a hole. We're going to here, just while I have the picture, I'm going to orient this circle so that it is positively oriented, which in this case means it needs to be clockwise. It is the inside curve. So if we need a parameterization for that, we need to make sure that we think of that in that orientation. All right, so if we apply Green's theorem says the double integral over d of this function del q del x minus del p del y is equal to the integral of c1 of p dx plus q dy plus the integral over c2 of p dx plus q dy. Right, now I'm intentionally not writing the original function just to save some space, but the p dx plus q dy is that function negative y over x squared plus y squared dx plus x over x squared plus y squared dy. And notice that the integral that we want is this integral here. We want the integral over that original curve C1. And so we can solve this equation for that particular integral. So we have the integral C1 p dx plus q dy. And of course, that's going to equal the double integral over d of del q del x minus del p del y minus the line integral over c2 of p dx plus q dy. Right, so in order to find the value of the line integral I want, what we need to do is compute these two integrals, which we are able to do in both cases, and then just subtract the two values. And this will give us the desired line integral over the original curve C1. All right, so let's start with the double integral over region D of del q del x minus del p del y. All right, so we just need to compute these derivatives. We differentiate q with respect to x. So we're going to use the quotient rule. We're going to have 1 times x squared plus y squared minus x times 2x, so that'll be minus 2x squared, all over x squared plus y squared, quantity squared. And we're going to subtract from that the derivative of p with respect to y. So again, using the quotient rule, we have negative 1 times x squared plus y squared minus negative y times 2y. So that becomes positive 2y squared. And that again is over quantity x squared plus y squared squared, dA. Right? And if you compute this expression in parentheses, if you work it out, we do get exactly 0. So this is the double integral over d of the function 0. And of course, that is equal to 0. Right? So we needed to compute these two integrals and subtract their values. And so here we see the first integral is equal to 0. And in order to compute the line integral that we want, this leaves us to have to compute the line integral over curve C2. So we want to compute the integral over curve C2 of negative y over x squared plus y squared dx plus x over x squared plus y squared dy. Right, this is the integral we want to compute. And so the first thing we need to do is find a parameterization for C2. So what we need to remember about C2 is that it is a circle centered at the origin. And it has some radius, right? We didn't write what the radius was because we don't know. It depends on the curve. But it has some radius. So let's just call that radius A. And so if I have the circle centered at the origin with the radius of A, then I can quite easily parameterize this using the following vector function. We could have A cosine of t and negative A sine of t, and t ranging from 0 to 2 pi. Okay. Now the a here, the coefficient of cosine and sine of t, the a corresponds to the radius a of our circle. And it might surprise you that the y component here, the negative a sine t, is actually negative. But remember that we want C2 to be oriented to go clockwise. All right, if I just did a cosine t, a sine t, I would have a counterclockwise parameterization of that curve. So because this is the inside curve of our region, we want it to go clockwise. And so making the second coordinate, the second component, the one involving sine, negative is one way to do that. And so this is our parameterization that we can use for our line integral function above. The nice thing about this too, so I don't have to write it up there to save some space, notice that in this parameterization, we have x squared plus y squared in those two denominators of our scalar fields that we're going to need to compute. Notice that x squared plus y squared is simply a squared. All right, we're going to have a squared cosine squared plus a squared sine squared. We can factor out the a squared, and of course cosine squared plus sine squared is equal to 1. So x squared plus y squared is going to equal a squared. That'll make our life a little bit easier as we compute this line integral. Right? And so going back up here to the top, this line integral is going to be the integral from 0 to 2 pi of negative y. So negative y is going to be a sine of t over x squared plus y squared, which is a squared, multiplied by dx. So dx is going to be negative a sine of t. And then we're going to add to that x, and we're going to have to add that below. I apologize for space. So we have to add x, which is a cosine of t, divided by x squared plus y squared, which is a squared, multiplied by dy, which is going to be negative a cosine of t. And all of that dt. Right? And so when we go to simplify all of this, we see what we get is in this case the a's will all cancel. So we have negative sine squared of t. And again over here we have all the a's canceling. So we get minus cosine squared of t dt. And of course, negative sine squared minus cosine squared is just, we could factor out that negative and just get sine squared plus cosine squared, which is 1. So this is just negative 1 dt. And so we get negative 2 pi minus 0 as our value for this integral. Right? And so putting this all together, right, we wanted the integral of c1 of this particular function, negative y over x squared plus y squared dx plus x over x squared plus y squared dy. Using Green's theorem, we saw this was the double integral over d of this function dq dx minus dp del p del y minus the integral over that circle, C2, of our function negative y over x squared plus y squared dx plus x over x squared plus y squared dy. And we've computed both of these integrals on the right-hand side. We saw this first integral was equal to 0. We saw this second integral was negative 2 pi. And so we have 0 minus negative 2 pi, which is positive 2 pi. And this is the integral that we wanted. Now, what we just did might not seem impressive to you, but if you go back and remember what the curve C1 was given to be, you'll remember that it wasn't a fixed curve in the plane. It was some arbitrary closed simple curve that contained the origin. So other than the basic kind of geometric properties of being simple and closed and positively oriented, the only real thing that we knew about this particular curve is that it contained the origin. And other than that, it could be pretty much anything. And so what we've just done here is for this particular vector field, this negative y over x squared plus y squared, and x over x squared plus y squared. For this vector field, we've shown that the integral of that line integral of that vector field over any curve containing the origin will be exactly 2 pi, and without knowing anything at all about that curve. And so in a lot of cases, this is one of the nice, strong, one of the main uses for Green's theorem is that we can compute integrals of vector functions over curves without actually knowing a parameterization for the curve. In this case, what we were able to do is because we knew it contained the origin, we were able to remove a circle around the origin of some radius, and we were able to use the fact that we know a parameterization of a circle in order to compute this desired integral. And so this is one of the really strong aspects of Green's theorem, is that you can use it even if you don't think you have all the information that you need. And this is a perfect example of that kind of a situation.